terms in the expansion of 1 minus 2x to the power 5. We know formula is 1 plus nc1 b to the power 1 plus nc2 b to the power 2. Three terms. So the first three terms will be 1 nc1 b power 1 and nc2 b power 2. 5c1 minus 2x to the power 1 plus 5c2 5c1 is 5 times minus 2x. X plus 40x squared. So these are of x squared in the expansion of 1 plus ax plus 2x squared, 2x to the power 5. So we already know that the expansion of 1 minus 2x to the power 5 is 1 minus 10x plus 40x squared. And the coefficient of x squared is 12. So first we need to, when we multiply, we get an x squared. So we have 1 times 40x squared will be 40x squared, ax 10x, ax squared, and will be plus 2x squared is square will be 12x is 12. Now taking x squared common, we'll get 14 minus 10x 42 minus b is equals to 3.
In question 2, it says that a point is moving along the curve y is equals to 2x plus 5 upon x in such a way that the x coordinate is increasing at a constant rate of 0.02. Now, x coordinate is increasing at a constant rate of 0.02 implies that dx upon dt is equals to 0.02. We have to find the rate of change of y, which means dy by dt is an unknown. And the value of x is given as 1. Now, we know that dy dt is equals to dy dx multiplied by dx dt. To find dy dx, we'll use the equation y is equals to 2x plus 5 and we'll bring the x in the numerator, so this will become minus 1. Finding the dy dx, we'll get, so derivative of 2x will become 2. For 5x power minus 1, we'll multiply minus 1 by 5, which will become minus 5. And decreasing the power by 1, we'll get minus 2. We'll write it as 2 minus 5 upon x squared. Substituting the value of x, which is x equals to 1. So 2 minus 5 upon 1 squared will be 2 minus 5, which is equals to minus 3. Substituting the value of dy dx into the equation, we'll get dy dt is equals to minus 3 times 0.02. So the final answer will be minus 0.06 units per second. In question 3, a curve is such that the dy dx is given. The point 1, 1 lies on the curve. We have to find the coordinates of the point at which the curve intersects the x-axis. Now, the x-axis implies that the value of y will be 0, so the coordinate will be x, 0. Now, to find the x value, we need the equation of the curve first. To find the equation of the curve, we'll integrate the expression of dy dx. So this will become dy is equals to 12 into 2x plus 1 to the power minus 2. We'll bring the 2x plus 1 whole square in the numerator, dx, and we'll put the integration sign. Integrating this, we'll get y is equals to 12 into 2x plus 1. Increasing the power by 1, this will become minus 1. And we'll divide by minus 1 and multiply it by the derivative of 2x plus 1, which is 2, plus c. Simplifying this, this will become y is equals to minus 6 upon 2x plus 1 plus c. So we'll bring the 2x plus 1 to the power minus 1 in the denominator to make it the sign positive. Now to find the value of c, we'll substitute the points 1, comma 1 as they lie on the curve. So this will become 1 is equals to minus 6 upon 2 times 1 is 1. So 2 plus 1 will become 3 plus c. So minus 6 upon 3 is minus 2. So c will be 1 plus 2, which is equals to 3. Now we have the equation of the curve, which is y is equals to minus 6 upon 2x plus 1 plus 3. The coordinates of the point at which the curve intersects the x-axis means we'll substitute the value y is equals to 0 into the equation. So we'll get y is equals to 0 is equals to minus 6 upon 2x plus 1 is equals to plus 3. Bringing the 3 on the other side, we'll get minus 3 is equals to minus 6 upon 2x plus 1. The negative signs will cancel out. Now we can simply cancel 3 by 6. So this will become 3 one times and 3 two times. Cross multiplying, we'll get 2x plus 1 is equals to 2. 2x is equals to 2 minus 1, 1, and x will be is equals to half. So the coordinates will be half, comma 0. Now, even if we had multiplied 2x plus 1 by 3, this would have become 6x plus 3 is equals to minus 6 is equals to plus 6. So 6x is equals to 3. And again, we would have gotten x is equals to 1 upon 2. So these are the coordinates when the curve crosses the x-axis. In question 4, we have to prove the identity sine theta plus cos theta multiplied by 1 minus sine cos and prove it as sine cube plus cos cube. Now, the simplest way to prove any identity is to apply basic algebraic operations and then to apply any identities that we know. So, expanding the bracket, we'll get sine theta times 1, which is sine theta, minus sine theta multiplied by sine theta cos theta, which will become sine squared theta cos theta. Cos theta multiplied by 1 will be cos theta, minus cos theta multiplied by sine cos will become cos squared theta sine theta. Now, as we need to bring it to sine cube and cos cube, we need to look for the identity where sine squared can be written as 1 minus cos squared and cos squared is written as 1 minus sine squared, as we know that sine squared plus cos squared is equals to 1. So we can rearrange this to sine theta minus sine theta cos squared theta, and we can write plus cos theta with minus cos theta sine squared theta. Taking sine common, we'll get sine theta bracket 1 minus cos squared theta plus taking cos theta common out, we'll get cos theta into 1 minus sine squared theta. Now we know that 1 minus cos squared can be written as sine squared. So this will become sine theta multiplied by sine squared theta and cos theta multiplied by, so 1 minus sine squared will become cos squared theta. So this will become sine times sine squared is sine cube theta and cos theta times cos squared theta is cos cube theta. In the next part, we have to solve the equation sine plus cos times 1 minus sine cos is equal to 3 cos cube. Now we have proved that this expression can be written as sine cube plus cos cube, and this is equals to 3 cos cube. Simplifying this, we'll get sine cube is equals to 3 cos cube minus cos cube, which is 2 cos cube. Bringing the cos cube on the left hand side, we'll get sine cube divided by cos cube is equals to 2. We know that tan theta is equals to sine upon cos. So sine cube upon cos cube will become tan cube theta is equals to 2. So we can write tan theta is equals to cube root of 2. And finally, theta will be is equals to tan inverse of cube root of 2. Putting this value in the calculator, tan inverse of cube root of 2, we'll get theta is equals to 51.6. Now we know that tan is positive in the first quadrant and the third quadrant. So this basic angle, which is 51.6, will be made over here in the first quadrant and the third quadrant. So finally, our values of theta will be 51.6 and the other value will be 180 plus 51.6, which will be is equals to 231.6. In question 5, it shows a kite OABC in which AC is the line of symmetry. We have to find the equations of AC and OB. Now we know that if it is a kite, this line OB will be perpendicular to the line AC. Now the gradient of AC will be, so the gradient of AC will be y2 minus y1. So we can write it as 0 minus 4 divided by 8 minus 0. So this will be minus 4 upon 8, which is equals to minus 1 upon 2. We know that the formula for the equation is y minus y1 is equals to m into x minus x1. We have the coordinate 0, 4 and 8, 0. We can use either one of them. So using the coordinates of C, which is 8, 0, the equation will become y minus 0 is equals to negative 1 upon 2 times x minus 8. Cross multiplying and simplifying, we will get 2y is equals to minus x plus 8. For the equation of OB, as we know that the lines are perpendicular, the gradient of line AC is minus 1 upon 2. So the gradient of the perpendicular line will be positive 2. We have the coordinates of O, which is 0, 0. So to find the equation, we'll write it as y minus 0 is equals to 2 times x minus 0, which will be is equals to 2x. So the final equation will be y is equals to 2x for equation of the line OB. In the next part, it is asking us to find the coordinates of B. Now to find the coordinates of B, we know that this point, the intersection point of OB and AC, is the midpoint of OB. So to find the intersection point, we can first solve the equations of AC and OB simultaneously. So we'll get y is equals to 2x as the first equation, and the second equation was 2y is equals to minus x plus 8. Solving them simultaneously, we'll just substitute the value of y is equals to 2x into the second equation. So we'll get 2 times 2x is equals to minus x plus 8. So this will become 4x is equals to minus x plus 8. 5x is equals to 8. So x is equals to 8 upon 5. So the value of y will be y is equals to 2 times x, and as x is 8 upon 5, the value of y will be 16 upon 5. Now these coordinates, which are 8 upon 5 and 16 upon 5, are the coordinates of the midpoint of OB. We have the coordinates of O, which is 0, 0. The coordinates of B is x, y, and the midpoint coordinates are 8 upon 5, 16 upon 5. We'll apply the formula for midpoint, which is x1 plus x2. So we can just write x1 over here and y1, and x2 and y2 with the coordinates of B. So 0 plus x upon 2, comma 0 plus y upon 2 will be is equal to the midpoint, which is 8 upon 5 and 16 upon 5. Now equating the x coordinate with 0 plus x upon 2, we'll get 8 upon 5 is equals to x upon 2. So x will be is equals to 8 times 2, 16 upon 5, which is 3.2. And 16 upon 5 will be is equals to the y coordinate, which will be 0 plus y upon 2. So y will be is equals to 32 upon 5. And we can write it in decimal form as 6.4. So the coordinates of B are now 3.2 and 6.4. In the diagram, we have a circle with center O and radius r centimeter. The points A and B lie on the circle, and AT is a tangent. We have to express the area of the shaded region in terms of r and theta. Now the tangent to the radius will mean that this angle will be a right angle. To find the area of the shaded region, we will subtract the area of the triangle. So we can write it as, it will be is equals to the area of triangle AOT minus area of the sector AOB. Now, to find the area of the triangle in terms of r and theta, we have the length of AO. To find the length of AT, which will be the base of the triangle, we can use tan as, let's say this is x, so tan theta is opposite over adjacent, so tan theta will be x upon r. So the value of x will be r theta. Now the area of the triangle will become, so area of triangle will be equals to half base into height. So half into r into this, the length of AT, which is r tan theta. The area of the sector AOB, so we know that the area of a sector is given by half r squared theta. So the area of sector AOB will be is equals to half r squared theta. Finally, the shaded region will be the difference of the two areas. So the area of shaded region will be is equals to half r squared tan theta minus half r squared theta. In part 2, the question is asking us to find the perimeter of the shaded region, and the value of r is 3 and theta is 1 upon 2. Now the shaded region consists of 3 parts. So we have this arc length, which is AB. We have the length of AT and the length of BT. Now to find the length of BT, we can find the length of OT by Pythagoras theorem and subtract it from the radius. So first what we'll do is we'll find the length of the line OT. So OT is the hypotenuse, so OT square will be is equals to AT squared and plus AO squared. Now we know that AT is r tan theta, so we can write it as 3 tan of 1.2 whole squared plus AO, which is r, so this will be 3 squared. So OT, after applying the Pythagoras theorem, taking the square root of this value, the length of OT will be 8.279. Subtracting this from the radius, so we know that the radius is 3. So the length of the line BT will be 8.279 minus 3, which will be is equals to 5.279. Now to find the arc length, we know that the formula is S is equals to r theta. So r is 3 into 1.2. Finally, we'll find the sum of all the 3 sides. So the perimeter will be is equals to 3 into 1.2, which is 3.6, plus 5.279, plus r tan theta, which is plus the length of AT, which is r tan theta. So the length of AT will be 7.716. Finding the sum will be equals to 16.6 centimeters. In question 8, we have a geometric progression that has a second term of 12 and a sum to infinity of 54. We have to find the possible values of the first term of the progression. We know that the nth term of a geometric progression is given by a r to the power n minus 1. As the second term is 12, we can write it as 12 is equals to a into r to the power 2 minus 1. So this will become a r to the power 1 is equals to 12. So this is our first equation. We have been given the sum to infinity as 54. The formula for the sum to infinity is a upon 1 minus r. So this can be written as 54 is equals to a upon 1 minus r. We can rearrange it to make it a is equals to 54 into 1 minus r. And this is our second equation. Now we'll use this value of a from the second equation, a is equals to 54 into 1 minus r, and substitute it into the first equation. So this will become 54 into 1 minus r in place of a multiplied by r is equals to 12. Expanding this, we'll get 54r minus 54r squared is equals to 12. We can rearrange this equation, make the r squared term positive, and this will become 54r squared minus 54r plus 12 equals to 0. Using our calculators to solve this, we'll get the values of r as 2 upon 3 and 1 upon 3. Now to find the value of a, we'll substitute these values of r in the equation. A is equals to 54 into 1 minus r. So this will become a is equals to 54 into 1 minus 2 upon 3. And for the second value of a, we'll substitute 1 upon 3. So this will become 54 into 1 minus 1 upon 3. So putting this value in the calculator, we'll get one of the values of a as 18, and the second value of a will be 36. Now in part B, we have the nth term of a progression, which is p plus qn. The sum n is Sn is the sum of the first n terms. We have to find an expression for p, q, and n for the sum of n terms. Now, first of all, we need to understand that this p plus qn is a formula for an arithmetic progression. Now, just to give you an example, let's say if we have a sequence 3, 5, 7, 9, we can form the formula for the nth term by first finding the difference. So this is 2, so we can write it as 2n, and then subtracting the difference from the first term. So the first term was 3, subtracting 2 from it, we'll get 1. So this is the formula for the nth term. Well, this is a shortcut to find the nth term. Now, looking at it, we can see that this 2 is the common difference, and the sum of these two is always the first term. So from over here, we can say that p plus q will be is equals to a, and the common difference will be is equals to q. So d is equals to q. Now we have to find this expression for the sum of n terms. Now we know that the sum of n terms is given by the formula n upon 2 into 2a plus n minus 1 into d. Now in place of n, it will remain as n upon 2. In place of n, we'll substitute p plus q, and in place of d, we'll substitute q. Simplifying this, we'll get sum of n terms is equals to n upon 2 into 2p plus 2q plus qn minus q. So 2q minus q will become q. So finally, this sum of n terms can be written as n upon 2 multiplied by 2p plus qn plus q. Now in the second part, it is saying that the sum of 4 terms is 40 and the sum of 6 terms is 72. We have to find the values of p and q. Now as we have two unknowns, we'll form two equations and solve them simultaneously. So if the sum of 4 terms is 40, we will write the equation as 40 is equals to 4 upon 2 into 2p plus, so n is 4, so this will become 4q plus q. Simplifying this will become, so 4 divided by 2 is 2, and then 40 divided by 2 will become 20 is equals to 2p plus 5q. And as the sum of 6 terms is 72, we will write this as 72 is equals to 6 upon 2, so that will become 3 into 2p plus 6q plus q. Simplifying this will become 6p plus 18q, or we can add 6q plus q, that will be 7q. So 3 times 7 will become 21q is equals to 72. Now we can use our calculators to solve these two equations simultaneously, and we'll get the values of p as 5 and the value of q as 2. In question 9, we have two functions f and g. In part 1, we have to find the points of intersection of y equals to f of x and y equals to g of x. To find the points of intersection, we'll solve their equations simultaneously. So we'll write the function f of x, which is half x minus 2, is equals to g of x, which is 4 plus x minus half x squared. Taking the LCM on both the sides, we'll get x minus 4 upon 2 is equals to 8 plus 2x minus x squared upon 2. The 2's can cancel out, so the equation will be x minus 4 is equals to 8 plus 2x minus x squared. Making the x squared term positive, we'll bring the terms on the right hand side to the left hand side, so this will become x squared minus 2x plus x minus 4 minus 8 equals to 0. So the equation will be x squared minus x minus 12 equals to 0. Factorizing and solving, we'll get the values of x as x minus 4 times x plus 3 is equals to 0. The values of x are x equals to 4 and x equals to minus 3. To find the value of y, we can substitute these values of x in either one of the two equations. So as the equation for f of x is simple, we'll use this one. So this will be half into x. So one of the values of x is 4 minus 2. So 4 upon 2 is 2. So f of x will be equal to 0. So one of the coordinates will be 4 comma 0. And we'll use the other value of x, which is minus 3. So f of minus 3 will be half into minus 3 minus 2. So minus 3 upon 2 minus 2 will become minus 3.5. So the other point of intersection will be minus 3 and minus 3.5. In part 2, we have to find the set of values of x for which f of x is greater than g of x. Now in the first part, when we equated the two equations, we got the final equation as x squared minus x minus 12 equals to 0. And the x coordinates were x equals to 4 and x equals to minus 3. If you represent this on a graph, this point would have been 4 and this point was minus 3 as it is equals to 0. Now when it says f of x is greater than g of x, it means we are looking for values of x that will give the result greater than 0. Now we know that this is the positive region and this is the negative region. We can see that moving forward from x, this will be greater than g of x. So we'll write x is greater than 4 and going backwards from minus 3, it will give us a positive value. So x will be less than minus 3. In part 3, we have to find an expression for fg of x and then reduce the range of fg. So to find the expression for fg of x, in the function f, we will substitute the function g. So the function f was half x minus 2. So we'll write half, and in place of x, we'll substitute the function g, which was 4 plus x minus x squared upon 2, and the minus 2 will remain outside. So multiplying half by 4, we'll get 2 plus x upon 2 minus x squared upon 4 minus 2. 2 and minus 2 will cancel out. So the final answer for fg of x will be minus x squared upon 4 plus x upon 2. To find the range of f of g, as it is a quadratic equation, we can complete the square and find the turning points, or we can find the gradient and put it equals to 0. So as at the turning point, so for a quadratic equation, we can have a minimum point or we can have a maximum point. At each of these points, the dy dx will be 0. As the x squared term is negative, so we'll have a maximum point. So first finding the dy dx of f of g, this will become minus 2x upon 4 plus differentiating x upon 2 will give us 1 upon 2. We'll put dy dx equals to 0. So this will become minus 2x upon 4 plus 1 upon 2. So minus 2x upon 4 is equals to negative 1 upon 2. The negative signs will cancel out. So this will become 2x is equals to 4 upon 2, which is 2. So the value of x is 1. Now once we have the value of x as 1, we'll substitute to find the value of f of g. So substituting x over here, we'll get minus 1 squared upon 4 plus 1 upon 2. So negative 1 upon 4 plus 1 upon 2. The value of the function fg will become, so this will be minus 1 plus 2, which is 1 upon 4. Now as this was the maximum point, the range of f of g will be less than or equals to 1 upon 4. In part 4, it has given a function h, which is 4 plus x minus half x squared, and the domain is x is greater than equals to k. We have to find the smallest value of x for which h has an inverse. Now, for the smallest value of x for which h has an inverse, again, we'll have to find the turning point. As for any function to have an inverse, it must be a one-to-one function. So if we have a quadratic equation, it will be a one-to-one function from this point of from the turning point. So to find the turning point over here, we can differentiate the equation again. So finding the dy dx of the function, we will get, so the derivative of 4 is 0, the derivative of x is 1, and the derivative of minus half x squared will become minus 2x upon 2. So this will become 1 minus x. Now at the turning point, the gradient is 0, so this will be 0 is equals to 1 minus x, or x is equals to 1. So for x equals to 1, this will be the smallest value of k, which is a value of x, for which this equation will have an inverse. In question 10, we have a curve with the equation y equals to x cube minus 2x squared plus 5x, which passes through the origin. In the first part, we have to show that the curve has no stationary points. Now, we know that at stationary points, the dy dx or the gradient is 0. So first of all, we find the dy dx of this equation. So the dy dx will become 3x squared minus 4x plus 5. We'll put the dy dx equals to 0. So this will become 0 is equals to 3x squared minus 4x plus 5. Now, to show that the curve has no stationary points, we have to show that there are no values of x for which this dy dx will be equals to 0. So rather than applying the complete quadratic formula, we can simply use the discriminant b squared minus 4ac. And if it is less than 0, it will prove that there are no values of x, or there are no roots for which dy dx will be equals to 0. So as b is minus 4, so we'll write minus 4 whole squared minus 4 times 3 times 5. So this will become 16 minus 4 times 3, 12 times 5 is 60. Now, as this is coming as less than 0, it proves that there are no values of x for which dy dx is 0. Now, in part 2, we have to find the gradient of the, we have to denote the gradient of the curve by m. So in place of dy dx, we'll write m is equals to, the expression for dy dx was 3x squared minus 4x plus 5. We have to find the stationary value of m. So to find the stationary value, that means we'll derivate the function m is equals to 3x square minus 4x plus 5. And then for the stationary value, we'll put it equals to 0. So dm upon dx will be is equals to 6x minus 4. For the stationary value, we'll put this equals to 0 is equals to 6x minus 4, and x will be is equals to 2 upon 3. To find the value of m, we'll substitute the x value in the original equation. So this will be written as m is equals to 3 times 2 upon 3 whole squared minus 4 into 2 upon 3 plus 5. Substituting these values in the calculator, we'll get our value of m as 11 upon 3. To determine the nature, we'll differentiate the function again. We'll find the double derivative. So differentiating m upon dx, again we'll get d square m upon dx square as 6. Now, as this is greater than 0, it shows that it has a minimum point. In part 3, we have to find the area of the region enclosed by the curve, the x-axis, and the line x equals to 6. The original equation was x cubed minus 2x squared plus 5x. So the equation was x cubed minus 2x squared plus 5x. To find the area, we'll integrate the equation, and this will be, after integrating, this will become x to the power 4 upon 4 minus 2x cubed upon 3 plus 5x squared upon 2. Now we know that the limits are from the line x equals to 6 and the x-axis. So this will be the So this will be taken as 0. Substituting the limits 6 and 0 in the calculator, we'll get 6 power 4 upon 4 minus 2 into 6 cube upon 3 plus 5 into 6 squared upon 2. As the lower limit was 0, so the whole term will become 0 as x power 4 upon 4. So 0 upon 4 minus 2 times 0 upon 3 plus 5 times 0 upon 2 will be 0. Substituting this in the calculator, the area will come out to be 270.